VPT Analysis of 11 Months Post-Stroke Recovery Energy and Trajectory Evolution Part 2, Number 1671, VPT 130, the 5th of June 2026, Gerald C. EclaireMD Foundation, Category Stroke. VMT Analysis Results. First, the correlations between the output strain of TSI-3B and the three selected input stressors are as follows: glucose equals 48%, PP equals 60%, SBP equals 12%. Other than the moderateky high correlation of 60% between PP and TSI-Stroke. Both glucose and SBP showed relatively weak correlations with my stroke risk. I did not want to spend additional time searching for deeper statistical meaning because statistical methods provide limited value within my math physical medicine research framework. My primary interest is not statistical correlation, but rather the physical interaction among the input variables and their combined effect on the output of stroke risk. My focus is on the interaction mechanism rather than the statistical association, which is a fundamental difference between my approach and a conventional statistical analysis. Second, the viscoplastic energy contributions to the output strain of TSI-3B from these three selected input stressors are as follows: glucose equals 30.7%, PP equals 34.5%, SBP equals 30.8%. Each of these three input stressors contributes almost equally to the TSI-3B output strain. This observation is particularly interesting because it differs from the correlation analysis discussed earlier. In the correlation analysis, PP showed the strongest association with TSI-Stroke, while glucose and SB exhibited much weaker correlations, however. From an energy contribution perspective, all three variables contribute nearly equal amounts to the final output strain. This finding suggests that statistical correlation and physical contribution are not necessarily the same thing. A variable may exhibit a relatively weak statistical correlation with the output while still contributing substantial energy to the system. Conversely, a stronger correlation does not automatically imply a dominant energy contribution. From a VMT perspective, the interaction among glucose, PP, and SBP appears to be more important than the individual behavior of any single variable. This observation is consistent with multiplicative structure of the TSI-3B model, where the output strain is generated through the combined interaction of all three input stressors. As a result, the system behaves more like an interconnected network than a collection of independent variables. Third, my accumulated viscoplastic energy levels were 20% in December to 102,561% in January 2026. Therefore, the period between December 2025 and January 2026 appears to represent the pivot point of my stroke recovery energy transition. During this interval, the accumulated viscoplastic energy increased sharply, indicating a significant shift in the overall system trajectory. Incidentally, my TSI-3B level increased from 93 in December 2025 to 96 in January 2026. Prior to December 2025, my TSI-3B generally remained within the range of 90 to 93. After January 2026, it shifted upward and remained within a higher but still stable range of 93 to 97. This transition is also visible in the graphical presentation, where the TSI-3B curve exhibits a noticeable upward jump between December 2025 and January 2026. The simultaneous upward movement of both the accumulated viscoplastic energy and the TSI-3B trajectory provides additional evidence that this period represents a meaningful pivot point in my stroke recovery pathway. From a VMT perspective, the significance of this pivot point lies not only in the increase of TSI-3B, but also in the apparent transition of the physiological system from one operating state to another. The observed change suggests a reorganization of the underlying system dynamics, after which the trajectory stabilized within a new range. Topological observations from the 3D scatter and 2D radar diagrams. In addition to the conventional time series analysis, I constructed a 3D scatter diagram using TSI-3B, glucose, and SBP, together with a radar chart containing TSI-3B, glucose, PP, and SBP. These topological graphical representations provide additional insights into the connectivity, trajectory evolution, and overall behavior of the physiological system from a mathematical perspective, including geometric movement paths, directional trends, data connectivity, geometric structure comparisons, pivot points, and dynamic changes occurring throughout the system trajectory. The 3D scatter diagram reveals that the physiological system did not move randomly through the state space. Instead, The data points followed a connected trajectory. During the early recovery period from August through December 2025, the system occupied a relatively compact region characterized by lower glucose levels and lower TSI-3b values. Between December 2025 and January 2026, the trajectory underwent a noticeable transition and moved toward a different region of the state space. This observation is consistent with the pivot point between 12/25 and 01/26, identified earlier through the viscoplastic energy analysis. The transition was not simply a change in one biomarker. Rather, multiple variables moved together and produced a new system configuration. The trajectory therefore suggests a coordinated state transition instead of isolated variable fluctuations. The radar chart provides a different perspective. Instead of displaying the movement through time, it illustrates the relative balance among the four variables. The shapes associated with different months demonstrate that the physiological system continually reorganized itself during recovery. The geometric pattern expanded and contracted over time, indicating shifts in the relative contributions of glucose, PP, SBP, and TSI-3b. One particularly interesting observation is that PP remained relatively stable compared with glucose and SBP. This finding is consistent with the physiological interpretation that pulse pressure PP reflects vascular aging and arterial stiffness, characteristics that evolve slowly and exhibit much smaller variations over time. In contrast, glucose and SBP exhibited larger dynamic changes and therefore contributed more strongly to the short-term evolution of the system trajectory. From a VPT perspective, the most important observation is not the absolute value of any individual variable. Rather, it is the connectivity among variables and the evolution of the overall system configuration. The 3D trajectory and radar patterns both suggest that stroke recovery behaves more like a dynamic, interconnected network than a collection of independent biomarkers. The topological significance lies in the preservation and evolution of connectivity. While individual biomarker values rise and fall, the relationships among variables remain connected through a continuous pathway. This behavior supports the concept that stroke recovery should be viewed as a trajectory moving through a multidimensional state space rather than as a sequence of isolated measurements. Therefore, the topological diagrams provide visual evidence that complements the viscoplasticity analysis. Both approaches identify the period between December 2025 and January 2026 as a critical transition region. The energy analysis identifies the pivot point quantitatively, while the topological diagrams reveal the corresponding reorganization of the physiological state space. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.